Moving to our next topic, which is on critical level measurement. And to present this topic, I would like to call Mr. J. Victor George, Srirang Automation and Controls. Let's talk about Mr. George Moore, engineering professional in electronics and communication, having 15 years of experience with a portion dedicated to calibration, showcasing a commitment to precision and quality in all endeavors, and a decade of experience in sales of process automation sensors. Ladies and gentlemen, with a big round of applause, Mr. J. Victor George.
So thank you, ISA, for this opportunity. And the topic that I'm going to talk today about is critical level measurement. What we mean by critical level measurement? The level measurement in any industries, it could be due to the level measurement that is very crucial because it could directly affects the revenue of the company, or the critical level measurement, which means it is really difficult because of the harsh environment. Maybe it could be due to the vapors, high temperature, and it could be due to various other reasons. We are Srirang Automation and Controls, a distributor of Ametek Drexel-Brook. Ametek Drexel-Brook is based out of Hersham, USA. They have their manufacturing facility there. We are the distributor of them. They manufacture very good level measurement solutions. So in this critical level measurement, I'm going to talk about the level measurement technologies that are currently available and working principle of RF admittance. This is what we are specialized in, and why this RF admittance is suitable for critical applications that I'm going to explain. And then there are some disadvantages in RF admittance, RF capacitance, how we are overcoming as a Drexel-Brook. And I'm going to talk about two applications where our sensors are successfully installed and working well. So currently, the major technologies that are available for level measurement is radar, ultrasonic, displacer type, float, and capacitance. And we call our product as RF admittance, which is eventually a capacitance measurement, but however, we call it as RF admittance. I'll explain you later why we are calling it as RF admittance. So as we all know, the radar technologies are common right now, and many of the applications we are using radar because of its non-contact in nature and very good in level measurements. Then ultrasonic is also non-contact type. Displacer types are used in few applications where the solids and powder applications. Then float is very common in any industries. Then another one is the capacitance. I'm going to talk about the RF admittance and why this RF admittance is very crucial in critical level measurements. To move further, I'm just going to talk a little bit about the capacitance measurement with a very basic terms. We might have seen this small device, which is there in the left side picture on the bottom. This is a capacitor. In every circuit boards, we might have seen this. To create or to form this capacitor, we need three components, two conductive plates, one dielectric medium. That forms the typical capacitor. And what happens in real world, in a level applications, while you are using the same technology? We are creating a capacitor, a big capacitor with a vessel, where you are installing a transmitter or a switch. So if you look at the right side picture, it is an installation and cross-section view of an installation level transmitter, where to create a capacitor, what we need? We need two conductive plates. So one is the conductive plate. One conductive plate is the tank wall, which should be a conductive wall, in metallic wall, I would say. Then the center rod, which is from the transmitter. So in between that, the dielectric medium should be there. That is the actual measuring medium. So be it water, oil, or any kind of liquid, that is the dielectric medium. So all the liquids and solids have their unique dielectric constant. Like for example, air will have 1, oil has 2, water has 80. So similarly, every medium has its own dielectric constant. So factors that affect capacitance. So when you increase the dielectric constant, so which means if you are changing the liquid, so then the total capacitance, measured capacitance will change. And then when you increase the area of the plates, like if you change the dimension of the tank, then the measured capacitance will change. At the same time, if you decrease also vice versa, it will change. How are we calculating it? The basic formula for calculating a capacitance is K, which is a dielectric constant, and area of the plates. Here in level measurement, area of the place what we are measuring, and D is the distance between two plates, which is a tank wall and a transmitter probe. So with this formula, we can calculate the capacitance. So how this has been implemented in level measurement. So this shows the installation of a level transmitter in an empty tank. The first picture, if you see, in an empty tank, for example, we get 20 picofarad. We measure capacitance in picofarad value. So we get 20 picofarad, and that has been set as 4 milliamps, which is a zero level because there is no level. And you are pouring some liquid, let's say water. And when as the water level rises, the output capacitance, what we are measuring through the transmitter, also rises. So at full level, when you reach the top level, you get at 30 feet, you get 125 picofarad, and that becomes the span. This is as simple as that. So this is how this has been calibrated. But one common problem with this technology is, what if the medium is sticky? If there are some sticky materials there on the vessel, and we have to measure that, it will remain there on the probe even though actual level comes down. So to overcome this, as Amatec Drexelbrook level measurement solution has found out a unique technology which is called Coat Shield. This is a patented technology by Amatec Drexelbrook. So in this picture, first picture shows the installation of level switch without the Coat Shield technology. So in this case, as the level rises and touches the probe and it comes down, but still there are some liquid or the sticky medium left over on the probe, which creates the wrong signal, so you get an alarm, even though there is no high level. So you get a high level alarm. What we did is, the center picture you can see, there are three components in our sensor. It's a 3-terminal probe, we call it, a ground and a coat shield and center wire. So the coat shield, as the name suggests, it is a shield against the coating. So it is not done physically, it is done electronically. So what we do is, if you look at the coat shield portion and the center wire portion, these two are two independent probes. And what we do is, we maintain the same potential at these two probes. So when there is no potential difference, there will not be any current flow. So as the second picture shows, when there is a sticky material left over on this, there will not be any current flow from the center rod to the ground through the current pathway of the sensor. The current pathway will be from the sensor rod and the tank wall and to the ground. So it always measures the actual level. It will not measure the sticky medium. So of course, while installations, we are suggesting few considerations, like the nozzle should be 45-degree angle, then it would be better. And the coat shield length, what we call it as a coat shield, so the length should extrude beyond the nozzle length. So we get a better installation and better coating rejection. This is how this coat shield technology is implemented in level switches. And in transmitters, it is implemented in a little different way. So in a level transmitter, as this picture shows, what we get is, when you analyze the signal, we get three signals. One is RF signal. The RF signal is nothing but a radio frequency wave, which we generate through our electronics to measure the capacitance. That is why we call it is RF, radio frequency signal. And apart from that, we get two more signals, that is resistive current and one is capacitive current, because of this coat shield probe technology. And when you analyze resistive current and capacitive current, these two are opposite in phase. So with a filter, we can eliminate that because we are identifying what is resistive current and what is capacitive. We can analyze only RF signal, and with this RF signal, the actual level is being measured. So this is how the coating error is eliminated in level transmitters. So there are few applications where this RF admittance technology works really well, one of which is interface level measurement in a desalter. So in desalters, it is always mandatory to have the interface level at some particular level. So the primary aim is to controlling the interface level so that the oil does not go through the water dump valve. What we are doing is here, the level transmitters that we are putting inside the interface level inside the desalter, it actually measures only the water level. It does not measure the oil. That is how we calibrate it. How we are calibrating it? If you look at this picture, the water dielectric constant is 80, and oil has 2. In real world, what we do is, we fill this tank with the actual oil and to the top level. So you measure the capacitance with our transmitter, and we get some particular capacitance value, that becomes 0. We'll make that as a 0 level. So the complete oil becomes 0 level. And then again, we pour the water, and it becomes, we get some picofarad value. Let's say we get 800 picofarad, and that becomes the span level. So whenever there is a oil, there will not be any measurement. It shows the 0. But the moment water enters, it started reading, because oil, we made it 0. So that's how it measures accurately the interface level. There are other technologies used in desalters like GWR. The advantage of using RF admittance is that in GWR, if there is an emulsion layer in the desalter, if the emulsion layer thickness goes beyond certain level, GWR will give you the top level of emulsion. It will struggle to get the actual water level. Whereas in RF admittance, because water is conductive in nature, we call it as aqueous phase, oil is insulating phase. So what this RF admittance do is, it measures only the aqueous phase. So we always measures only the water after calibration. So that is why we are very successful in interface level measurements in desalters. So our product has all the approvals like ATEX, PESO, and it comes with HART protocol 4 to 20 milliamps for high temperature, and then high pressure ratings. The other one application, what I'm going to talk about today, is the water cut, or we can say it is water in oil. So the installation will be like this, on the vertical pipe and also in the spool piece. So this is not the level measurement, it is quite different. What we are doing here is the water percentage in an oil. So that is what we are going to measure with this RF technology, RF admittance technology. So I'm taking one example of LACT skid, water in oil measurement. So in LACT skid, we transfer the oil from one place to another place through any pipeline or track or anything, through some different modes. So while transporting or while shifting from one place to other place, we need to know few characteristics of this particular oil. One of it is water percentage that are present in the oil, because that defines the oil quality as well. So in LACT, our water cut with RF admittance are working really well. How does it work? How we are implementing as a level transmitter to measure the water percentage. So in a vertical installation, if you see, like the same concept as I explained in the desalter, water has dielectric constant of 80 and oil has only 2. There is a huge difference. So in the pipeline, initially the oil is filled. So we measure the capacitance. Let's say in oil we get 8 picofarad. And suddenly, then after that, we are filling this pipe with water, and we get 35 picofarad. So 8 is the 0 percentage, 35 is maybe 50% as per this device. This device range is 50% and 30% and 80% range we have. So that we calibrate for 0 to span. So 8 is 0, 35 is span. This is for an example. So in real world, we'll get different picofarads depending upon the pipe size and characteristics. So there is one more problem here is when you are measuring precisely the water content, that there could be a chance that density and temperature could affect the measurement. So to solve this, Drexel has a DCM model, which is density corrected model, so which will accept density data from the Coriolis mass flow meter. So density and temperature can be given to the DCM model. So this will compensate the value and gives the actual water percentage. The advantage of having RF admittance for water measurement in oil is that you get larger measuring area, whereas in other technologies, like for measuring water content, there are other technologies available, which is microwave and some spectroscopy technologies are available. So compared to that, we have a larger area, sampling area, and it is online, like continuously you are monitoring it when the oil is flowing. It's not sampling method. We are just taking out and checking the water content for the particular batch. It's not like that. It is online. So that is one advantage. And high temperature rating, and we have 3-year warranty for this product. And one of the client in USA told us that they have taken return on investment in 2 years. And one disadvantage of having RF admittance technology for this measurement, beyond 50% in light oil, we cannot use this, and beyond 80%, we cannot use it. Because beyond 50%, it will become mostly aqueous phase. So the meter started giving you 100% value, though it will be 60% or say 80% of water, it will show you 100%. The same applies for 80% level as well. But however, in LACT skid kind of applications, the water percentages should be really low because it's an oil where you should not have any moisture. So you are going to measure only 0 to 1% or below than that. So in such applications, RF admittance is the best one, and for applications where water content is really high, beyond 50% or 80%, where microwave and spectroscopy is better. But for lower range of applications, RF admittance is the better one. Few installation pictures on this LACT kit and other applications, which I'm showing here. Apart from that, this particular product can be used in various other applications, automatic well testing, basic sediment, and separation vessels also we can use it. And one more thing, dielectric analysis can be done. For example, if you need a dielectric analysis of any liquid, which can be done with this RF admittance transmitter. See, as I explained, the capacitor formula is C is equal to Ka divided by D. So in a mathematical formula, if you know all the parameters except one, we can calculate it. So with our transmitter, we can measure the capacitance, we know the tank dimensions because our probe and other tank dimensions. With this, we can measure the area and distance also we can measure. So only thing, if you don't know the dielectric constant, then we can measure the dielectric constant. So if your liquid is not homogeneous, because you're getting a different liquids for your process, and you want to know the dielectric constant, that can be done with these RF admittance technologies. And then one more applications, machinery lube oil, that has to be moisture free though, so the moisture has to be measured. That also can be done. That's it from my side. Any questions?
Thank you very much, Victor. Any questions? Anybody has got any queries? Yeah, we have got.
The limitation will be on the dielectric constant. See, for example, you have a medium which is homogeneous, like you are not getting a different medium with a different dielectric constant. Then there is no issue. Temperature will not have much effect on level measurement because we can dampen the temperature effect, because it is not going to give you density, or temperature will not have much effect on level measurement. It will have effect only on the precise measurement of water content. That is the reason we are having a density and temperature compensated model. For level measurement, temperature and density will not affect anything. Only dielectric constant will affect the performance or the measurement a lot. You need to have a homogeneous liquid. In case if you are measuring a different liquids on the same vessel, then it is not suitable. We need to have a different setup. The dielectric constant should be same for the calibration. Then we need to recalibrate it. If you are changing the liquid with a different dielectric constant, then it has to be recalibrated, then it works. Only that is the concern. Hope that answers. No, coat shield does not have any temperature limitation. Coat shield is what we call it as, it is not a physical one. It is actually what we are doing is electronically we are eliminating the error signals. So to find out the error signals, we have the physical constructions. Like we introduce one more probe as a coat shield. That is also a SS rod, so which measures the other currents which is created by the coatings. So that we analyze and remove it in the electronic units.
Thank you very much, Victor.
Thank you.
Reshma, can you please?
Thank you so much. Now I request Mr. Rishikesh Bhagat to please come and do the honor for us. Please hand over the token of love, token of appreciation to Mr. Victor George. Ladies and gentlemen, let's have a big round of applause. Thank you so much, sir. Thank you.